This tutorial is about coding for potentiometers. In the description below this video you will find a link to the GitHub code repository that includes a wiring schematics, the bill of materials and detailed explanations for each line of code. You will learn how to dim an LED with a 12-bit timer and lookup table. You will learn how to select different modes and run other code at the same time. You will learn how to control a DC motor's rotation direction and speed. And you will get tips for a better use of the map function and filtering twitchy outputs. To keep it simple, we keep hardware to a minimum because the clever stuff happens as always in the code. Here's an overview of all parts in case you're not so familiar with them. You can find cheaper substitutes online for most parts. For setups 2 and 4, you get by with what's in a typical starter pack. For the LED dimming and motor circuits, you need the specified or equivalent components. The wiring of each setup isn't difficult. And for 2 and 4, you could use an online Arduino simulator like Wogwi or Tinkercad. Setup 1. Dimming an LED with a 12-bit timer and lookup table. Linear dimming goes against the human perception of brightness. Turning a dimmer knob halfway, 50% so to speak, would result in a brightness perception of 75%. Another problem is that using the standard 10-bit PWM output, which means duty cycle values of 0 to 255, will make the dimming look choppy, especially on the low end. To get around both problems, we use built-in timer 1 with 12-bit output, and instead of slow calculations in code, we use a pre-computed lookup table with exponential PWM duty cycle values. Another benefit is dimming with a frequency of 4 kHz, which means that there is no perceptible flicker. Look at the code with detailed explanations for how this is done. Setup 2. Selecting different modes and running other code at the same time. Turning the potentiometer knob selects a certain mode of operation. Pressing the momentary switch button starts running the selected mode's code. Each mode's code runs only once per button press and for a certain duration. Seconds, minutes, hours or permanently, whatever you need for your design. The code is not blocking other code, so you can select other modes running other code in parallel, as you can see in the serial monitor. Look at the code with detailed explanations for how this is done. Setup 3. Controlling a DC motor's rotation direction and speed. When you turn the potentiometer knob, you change direction and speed of the DC motor. However, you cannot start and stop slowly, as you can see in the serial monitor and from the motor's rotation. From a PWM value of just over 40, the motor starts running with a fair speed already. This is how all basic DC motors work. As you rotate the knob towards the center, you are entering what's called a deadband, a zone of values where the motor is not powered. Without a deadband, it would be difficult to have a clearly defined halfway position where the motor is off. You must also use a deadband with joysticks, because joysticks are twin potentiometers. Look at the code with detailed explanations for how this is done. Setup 4. Tips for a better use of the map function and filtering twitchy outputs. The first example may seem a bit boring, but it is important when you are mapping a large input range to a small output range, like when using a potentiometer as a switch or selector. Please look carefully at the serial monitor. You would think 1024 divided by 8 is 128, but it is not. The problem is that the map function uses integer math. So what you do is increment 1023 and 7 by 1 and the problem is solved. Please look carefully at the serial monitor. The next tip shows you how to study the analog input from a potentiometer or sensor that will always fluctuate a bit, as you can see from the spikes in the serial plotter. When you exclude value changes of 1, 2 or 3, depending on how much fluctuation you want to suppress, the analog input becomes nice and steady. The last tip is useful for filtering twitchy input to smoothen values. Take a look at the serial plotter, as we're using no capacitor, a 100 microfarad capacitor and a 1000 microfarad capacitor. A higher capacity means smoother reaction, but the reaction delay will also increase. Just pick a capacitor that gives you the profile you need. Look at the code with detailed explanations for how this is done. Like I mentioned in the beginning, the clever stuff happens always in the code. Every line of code is carefully commented, so you can learn the logic step by step. So please head over to GitHub and take a good look. Once you understood each principle, you can confidently code for your own designs with potentiometers and joysticks. And now it's your turn. Thank you for watching and listening.